Alright, what is going on? So I'm going to analyze how the code for solving the permutation sequence, which is a daily problem for today, June 20th. So basically this problem is just returning, given n, which n represents like the number of unique digits starting from 1 going till n, and you're going to find the permutations for this, but you want to find the kth permutation. So one obvious solution is to use, in Python, you can use the itertools permutations, and that is neat and all because that returns the permutations in order. But the time complexity for that is like n factorial, so it's very slow. It actually passes the test for this problem though, so you can do that. I did do that for my first submission. I can show you like the runtime was 2,000 milliseconds versus 36 milliseconds. It took up a lot more space too than my final solution. So okay, so how did I do this? So the final solution basically goes over this. So let's take this example. So this will be my example to show how my code will work. So we have n equals 4, k equals 10. So we want the kth one, and we have n equals 4. So I'm showing basically like the first 6 combinations you get. If you start with 1, these are all the possibilities you have. If your first digit is 2, these are all the possible permutations you have. So the idea is to use like recursion or a while loop to basically go through here. And let me see if I can open up a new. Okay, all right, it does let me. Okay, so then I'm gonna change size of this. 28. Okay, so then what we're gonna do is we're gonna say, so at the beginning n is equal to 4 and k is equal to 10, and I'm gonna create this count thing and initialize to be 0, and I'm gonna have some type of like factorial. This will be like a list that will contain all my factorials. So we'll keep an extra 1. Ooh, let's make this larger. We'll keep an extra 1 so that the indexing is easier, and then 2, and be 6 and 24. So that's what our factorials are. So if you want to find the factorial, so the factorial for 4 is fact 4. Okay, that's how that works. And then the other thing that I create is I create this digits list, which will go from 1, 2, 3, 4. So just basically all the digits that we have. And then, so we do it in a while loop. What we're gonna do is we're gonna take the current n value, and we're gonna like say, okay, let's say our first digit is 1. Now, for our first digit being 1, we have 3 factorial options left. That is, the reason why we have 3 factorial options is because we have 3 digits, and the number of permutations for 3 digits is 3 factorial. So if we do that, we'll say, okay, well, if we increment our count by this factorial, so we're kind of like incrementing our count by fact n minus 1 in a sense, if n is equal to 4. And then when we do that, we basically get what's it called? You'll get like count will be, I'll show for this example, count will be equal to 6, right? Because that's what that equal to. And we're like, well, 6 is less than k, so we know our first digit can't be 1. So we go to the next digit, which is 2. And, we still have 3 factorial options after 2. And for this digit, our count is now going to be equal to 12, which is greater than k. Because it's greater than, I'm really going to check if it's greater than equal to k. Because it's greater than equal to k, what we're going to do is realize that, hey, my permutation I'm trying to find is going to have the starting value 2. So we set 2. So we know our answer is going to be within this range over here now. So I'm going to do is I'm going to fix the 2, and then I'm going to go and remove my digits. So I update my digits to be 1, 3, and 4. And then I'm going to go and have 2, and then we're going to test out the 1, and we have 2 factorial now, in a sense. So once I find something greater than this, I'm always going to decrement my k and my n, and I'm always going to like start my index at 0 again, because I want to look through the digits here. So then we go to this 2, 1, and we're like, our count is, we start over the count back at 6, so we go to, it goes to 8 here. It's still less, so we go 2, 3. We don't do 2, 2 because we can't do repetition, so we take 2, 3. That's the next digit in my digits. So we take 2, 3, and it still has 2 factorial options for the 1 and the 4. So we get count equals 10. Well, this is equal to k, so we're going to fix this as a 2, 3, and then we're going to update digits to be 1 and 4, and we're going to take 2, 3, and we'll test out 1, and we'll have 1 factorial. And our count goes back to 8, so our count is 9 when we do this. Then we do 2, 3, 4, and we have 1 factorial, and our count is equal to 10. So since it's equal to 10, we're going to go to the next thing, and the digits is equal to just 1 now. And for this, we have 2, 3, 4, 1. Just recall that when you take factorial of, I've always been taking factorial in n minus 1, right? And at this point, n is equal to 1, so n is 0 here. So this is actually going to return a 1, which is perfect because I set a 1 here at my 0th position for my factorial, which works here because if you add it up, because the count will be equal to 10, and so count is equal to k, so you decrement n, but the loop stops because n is equal to 0 now. Alright, so let's look at the code. That's mostly the idea. I don't know if I explained that well though, but okay. So the code here, we have factorial here. So I create my factorial by using accumulate and using the operator .mul, which basically multiplies the previous number, and I want the iterable to be 1 to n plus 1. So this gives the factorial. This will give the digits and count in I, and this is my answer. So here's the while loop. So notice I want to do it as long as n is greater than 0. We get our current digit based off the I. We get our current factorial. We increment our count. If our count is greater than or equal to k, then we decrement that factorial that we just did because we just went above k or we were equal to k. So we want to decrement it back down. I hope that makes sense because we found out that our value is within that range. It's kind of like these are blocks because if you're in the range of 1 to 6, you're going to be in here. If you're in the range from 7 to 12, you're going to be in here. So when you get 12 for the count, you're like, well, that's larger, and so you're in this block. And that's basically what you do. You're like, oh, I'm in this block. Here, I'll show what I'm seeing here. So what I'm seeing is, I'll plug this in. So okay, so what I'm seeing here is that when we increment to 12 and we get above k, I realize that I'm in this block, right? But then we keep going and we go to the next options and we get the count is equal to 10, so it's equal to k again when we use the 3. So now I know that I'm in this block, and then finally we go to here and we get this count is equal to 10, and we're like, now I know that I'm in this block, and I mean, the program stops at this point. But yeah, that's like what the program does. So I guess I could say initially it thinks it's in anywhere in this entire block, which this will be longer. This will also have like 3 ... and also have 4 ... or x x x and 3x x x. So it all start with 3 or 4, but we never get that far because we already isolate that it's going to be, yeah, and then we isolate even further, it's in this range or it's in this range. Okay, where am I at? I'm here. Okay, so that's what this does. We always want to add this digit to our answer, and we pop from the digits, we decrement in, and we set I back equal to 0 because we start over with the digits. Then we continue because we don't want to bother incrementing I. We only want to increment I when we're not running through here. Yeah, so this works. So what's the time complexity for this? So one thing to notice is that basically we're going to run in times through the while loop because we're decrementing n by 1. So it starts as n equals whatever, 9. Then it goes n equals 8. So it's going to do that n times. But for each of those n times, we're incrementing the count by the factorial. And that could be kind of like, it could be, at worst case, it could take n time, I believe. So it'd be like, so I think it's like 1 plus 2 plus 3. That is like, we'll run through here 1, sorry. So we run through the while loop without incrementing n. We do it 1 time, then we do it 2 times. Then we might do it 3 times, and then we might do it like, oh, wait a second. I mean, you keep subtracting the count, but it seems to me that the time complexity for this, I'm kind of messing myself up here, but it seems to me that the time complexity is not too crazy though, because let's see here, oh man, this is bad. See, this is why I knew I was gonna have trouble analyzing the time complexity for this problem. So okay, so every time we increment the count, I noticed we increment the count 2 times. The worst case scenario is we could have incremented the count n times, right? That's the worst case. That is if it was going to be in this range, in the range where it starts with 4, right? And the worst case for the next one is that, so we could have had to increment it n times for the number of digits. And then the other case, it might be in the last version of this one, so it might be plus n minus 1, and then plus n minus 2, and it might go all the way to plus 1. Well, this is kind of like going in a reverse direction of 1 plus 2 plus 3 plus plus n minus 1. Again, this is kind of like the worst case, I guess. So like the worst case is this could end up running O of n squared times, because 1 plus 2 plus 3 plus n minus 1, you might remember that that's equal to, I think, like n over n plus, I might be messing this up, but it's something like this, right, which is approximately n squared. So you get like this time complexity. But there's also one other aspect here, which is the other aspect to realize is that, well, no, actually this is pretty good, but it's also kind of realize that this is kind of like the worst case. Like the best case is our number happens to be in the first range, so it runs 1, and then it runs through here, and it just keeps ending up being the first range. So then it's just like 1 plus 1 plus 1 in times, which is really just n. So I guess the best case would be n time complexity, and the worst case is n squared. Alright, what is going on? So I'm going to finish up this video. So I just realized that my code was, it was good, but there is a more clever way to do this, where I wouldn't have to do that awkward popping. Like I was popping from my, I was popping from the digits here, which is kind of awkward. There's one thing I could do though. see. So what I did here is, this is just another solution that I found from the discussions. And I just thought it was super clever, so I tried understanding it. I'm just going to explain what the solution is doing. And the person who did the solutions, his name was like, is here. So like Desheng too. So I gave him an upvote. Oops, and I just took away my upvote. I guess if you double upvote, oh, double negative is a, wait, no, double positive is a negative, I guess. Okay, but anyways, so analyzing this code, so this is kind of cool because you have one while loop. It looks like it's doing something very interesting. So he's using this div mod. Div mod is kind of an amazing function. It basically returns a tuple of the quotient and the remainder. So he's getting the quotient. The quotient is his index. The remainder is his k. Now, why would you want to do that? Why would you want a quotient? Why would you want the quotient to be your index? And also another thing, I don't need this up. Another thing is, I don't need that. Another thing is, why subtract this one from the k? Well, let's take a look at this. So, if we think about what he's doing, first off, n is equal to 4 at the beginning, and k is equal to 9, because he subtracts 1, right, if I'm using 10. So you subtract 1, and you also subtract 1 from the n, so you go to 3, right? Now what you want to know is kind of like what I did here, right? So I had this 3 factorial, which is equal to 6, and then I knew that when I added to the count, that value, it gave me 6, but then if I add 6 again, it gives me 12, and that was above k. Now the interesting thing is that I would decrement my count back down to the 6. So I decrement my count back down to 6, and then I would continue. I would update my digits list, and then I would update. I would test out the second digit, which would be the second digit, and I would use 2 factorial. My count would go to 8 because I would add the 2. But just notice what I did here. I added 6 2 times, right? But in reality, to figure out what range it was in, I was really just adding the first 6 and adding the second 6 kind of just told me it was in this patch where you start with a 2, which ranges from 7 to 12. But I mean, the cool thing you could do here is if you just take 9 divided by 3 factorial, which is the 6. So usually you add the 6, you get 1 as the quotient, right? You get 1 and you get a remainder. But this 1 is amazing because it tells me that in my digits list, I'm going to be looking at this index here, the 2. And it also tells me I'm going to be looking at this segment of numbers, of permutations, where we're starting with a 2. That's what the quotient tells you. The quotient could have been larger. Like if k was larger, we would have been in the range of 3s maybe, or we could have been in the range of 4s. And just think about like when would it start? If instead of 9, we know that this goes from 7 to 12. So what if we had 13? We know it should be in the range of 3, right? So we did 13 divided by 3. That would equal 4. Sorry, 13 divided by 6 would indeed equal 2. Yeah, so it would indeed equal 2. So we would get the remainder of 2, and it would tell us we're in this range. Actually, we subtract 1 from it too, so we would do 13 minus 1, so it'd be 12. I guess that's important to notice because if we just use the 12 here, and we did 12 divided by 6, we would actually get a remainder of 2, and that means that it would be in this segment, but that's wrong. So that's why you have to subtract 1 from the k, because you need to do the 11, and I guess it's because we're 0 indexed. But you can also see in this edge case why you would have to subtract 1 from k, because it just wouldn't work if k was equal to 12. It would say, oh, you're in this segment where you start with a 3, but you should actually be in this segment, and I guess that's because you're indexing from 0. But you get the quotient, you get the remainder. The remainder is kind of like the leftover. So like here, I would count as 6, right? So then I would say the count that's left is 4. That is, it's 4 less than k. So instead of like just keep incrementing the count up to k, just say that the k is, update the k and say like, oh, the k is equal to the remainder, which is 3 here, which makes sense, right? Because now you're going to be looking in this segment and you're looking for the third element, because you just went through 1, 2, 3, 4, 5, 1, 2, 3. You just went through 6, right? And you're looking for the 10th element. And when you went through 6, k should be equal to 4 now. Now, just notice that we are using k equals 3 because we're decrementing k by 1. And then we continue looking through. And then we're going to continue looking through this one. So it should be the third element in here. But the third element in here from 0 index would be this one. That would be the 4th element. It would be at the 3 if it's a 0 index. Okay, so then what we'll do is we take those updated k, we take the updated k, we decrement the n, so now we're doing 3 divided by 2, right? To figure out where's in here. This gives us 1, so that means the index is 1, which means that since our digits are now going to be 1, 3, and 4, that 1 kind of tells me that it's going to be this 3 here. It's going to be in this blue box. It's going to be in this segment, this blue segment. And now I'm coloring in red though, I'm kind of messing up the color. And the remainder is 1. And that's perfectly fine. So that will be our new k, will be 1. Which makes sense from the 0 index version, because it should be if this is 0, then this is the 1. So then we go to that, and we divide it by 1. 1 divided by 1 is, well, 1. So we get, so we know that we're going to put a 4 here. So the last digit is just literally just doing 0 divided by whatever, and getting a 0, and, you know, just returning this answer. So you can see how this kind of does it by doing the division. It's basically what I was doing, but it's so much, it's very clever. So yeah, I really like this solution. I feel like I learned a lot by analyzing it.